let's say that the process X, D-dimensional process X, solves the martingale problem for script L mu, where script L is some differential operator. But I restrict to differential can be integral differential also. If F0 has a law mu, so mu is the initial law, and for F in this twice continuously differentiable functions with bounded partial second order derivative, this object fxt minus 0 t script L fxs ds is a martingale with respect to the natural filtration. So the unique solution to this martingale problem, if we have two such solutions, they are very involved. So the script is called the extended generator because this extends the classical idea of generator from second-order theory. The previous approach to the earlier approach to Markov process. And if I say that the martingale problem for script L, now I have dropped the initial condition, initial major mu. So therefore, if it's the martingale problem for script L, Dirac at X is therefore that therefore for all possible X. So if regardless of the initial condition it's therefore, then I say that the martingale problem itself is therefore, and then the corresponding unique measures nicely patch up to your Markov process. Satisfy the Chapman-Colbert equation. So this is true, for example, that sigma is non-degenerate for a division, and actually I think this one error I have, not error actually, but omission I have to apologize for. This was a two-part talk on two problems. I chopped off the first part because that was 1 hour talk, and I realized that I have included writing the Spaghetti differential equation. We should have been there in the first place. Okay. So if the sigma is the diffusion matrix, if that's non-degenerate and Lifshitz and if it's bounded variable, then it's certainly well posed. Or if both M and sigma are Lifshitz, then even if sigma is non-degenerate, it's well posed. But if M and sigma are only continuous, then existence of a solution is guaranteed through take a discrete caricature and interpolate and pass to the limit, you get a solution. But there's no uniqueness. So this is a well-known fact. So in particular, an ordinary differential equation is a special case where if you put sigma equal to 0, and there's an exotic example of non-uniqueness in Philip Hartmann's textbook on ordinary differential equations, which is actually time inhomogeneous. Nevertheless, it's interesting for every initial condition, there are uncountably many solutions. And there are other standard counterexamples where you have non-uniqueness at initial condition 0 and so on, but this is the one. Okay, but you can characterize all solutions that's possible for X2 and further. So suppose you are considering an interval 0 to capital T, just take a succession of increasing stopping times, and each stopping time you tau I you take a solution from tau I to tau I plus 1, which may depend on everything up to tau I in whichever way you please. Certainly you get a non-Markov solution and can get a non-Markov solution. So if you take closure of all such solution measures, that's all measures. That's the Schubert measure. They're in chapter 12 of the book. Okay, so let's come to the problem I want to look at. So consider, so basically, let script A X or script A U be the law of all, sorry, the set of all possible solutions for initial condition X or initial measure mu. So this is non-empty, convex, and compact, and just because we're working with continuous coefficients, there is an additional solution, and convex compactness properties are follow from this equivalent statement of the martingale formulation that if you take a value of effective minus fxs minus s p of l of xy dy conditioned on sigma fit up to s is 0, which is equivalent to plugging in some g of everything up to s. Now this f and g are continuous, so this holds true under weak convergence at Corbin combination. So the solution set is non-empty, convex, and compact. Okay, so the problem of Markov selection is given this family A sub x, pick one solution for each x so that they nicely satisfy the Chapman-Colbert equation. So this classical solution due to Kirchhoff, which is also there in chapter 12 of Prof. is as follows. So what cloud does this take some countable separating class? Let's say let Ri be enumeration of positive rationals and Fi bounded continuous countable bounded continuous separating class in the sense that integral Fi d mu equal to integral Fi d mu dash for all I implies mu equal to mu dash. Then define this function as Gij gamma. Gamma is the law of x. So Gij gamma is the expected value of integral 0 to infinity e to minus RIT j xt dt. Okay. So this is a kind of countable family, but with two parameters. I just take them out as a single parameter family, like single graphic or whatever. So f1 is 2. I have a countable collection of functionals. I start with a0x as my solution set a sub x, and recursively define a m plus 1x as this the set of minimizers over gamma of fm of gamma. So I will start with all solutions from format state, minimize my first f1 on that, take the set of minimizers that will be compact with the continuous function, it's a continuous compact also, set the second function on take the second function minimize on the minimizers, and to keep getting the nested family of decreasing family of continuous compact non-empty subsets, the intersection is non-empty. And that has a fantastic property that okay, this I should mention. This is an interesting thing. So this gets preserved. You inductively prove that at any level m, if you take any stopping time tau and a solution x starting at time 0, which is in a m of x, then x tau plus dot will be in a m of x tau. This is a crucial step. And this is a kind of dynamic programming type argument. In the dynamic programming using controls, basically you have an optimal solution from 0 to t, and if you take some tau in between, then the solution from tau to t will be optimal for the remaining problem from tau onwards. One variation of one. So Kirov started out his life in stochastic control, so they nicely use this again and again to extract a nice Markov solution. So the final, yeah, so that's a infinite, there's a non-empty intersection, and one can just from a choice of Fi is the one make sure that it's a singleton. So we have a collection of single measures for each initial condition x, and so from that, what I have said about topic type previously, it's actually a strong Markov process. To extract a strong Markov process without any failure property appearing anywhere. And not explicitly used. So for the general case for martingale problem, this was needed for diffusions. You can find the extension in different input state. And the problem with this construction is that you don't know whether what you get is unique. It can depend on your choice of not only your choice of the functional issue, if I arise here, and also the order of minimization. It's not obvious that it's independent of that. So the question is the principal alternative possible? This is what I have been trying to peddle with immediate success. And it's motivated by this philosophy of Kolmogorov, which apparently never wrote down, but it's reported in this paper called Ergodic Theory of Chaos and Strange Attractors by Ekman and Durrell. They say explicitly that Kolmogorov never wrote it down. But the idea is that in case of trouble, I mean, the ill-posedness, just add some noise, which usually helps to regularize these things. And then let noise go to 0. Hopefully, there's a unique solution or a few solutions. Take that as natural solution or a physical solution because, quote unquote, there's always some noise somewhere. So this was one major application has been to stochastically stable equilibrium in evolutionary games where Foster and Young and others. Then viscosity solutions in control can also be interpreted this way because and now they don't use that approach, but I believe the initial intuition was add half Laplacian to the Hamilton-Jacobi equation, in which case it becomes the Hamilton-Jacobi equation for a deterministic control becomes Hamilton-Jacobi equation for a stochastic control, which is easier contrary to what one might think, because noise smoothens out things. And it has a classical solution, let the noise go to 0 and you get a unique limit Otherwise, the deterministic algebraic equation does not have, may not have limit. But you typically get a unique limit under, not always, but under reasonable conditions. That's the correct equation. Then our friend Shankar Shastri in Berkeley in his thesis had taken small noise limits to explain hysteresis in nonlinear electrical circuits. Okay, so this is what I want to talk about. So let's assume bounded to M and sigma and look at the backward homograph equation. And this is so this red is sort of a red because this I have justified it. So this is degenerate. So the classical solution may not exist, but the viscosity solution does under suitable conditions that I'll come to later. The idea is as follows: what I say, the homograph trick. Just to make part of sigma, let's say sigma epsilon is square root square root of sigma transpose plus epsilon I is non-degenerate. Consider the corresponding backward homograph equation. It has classical solutions, and it is clean sort of interpretation, conditional expression of x epsilon t given x epsilon small t equal to x. Then as epsilon goes to 0, it goes to suppose that under suitable condition goes to viscosity solution uniformly on compact, and something called comparison principle for viscosity solution is crucial for claiming the unique limit. So let x epsilon be the process corresponding to L epsilon for fixed initial law, and x one of its substantial limits. Then in this earlier work with Suresh Kumar, we showed that there is a fellow solution with the same one-dimensional marginals as x. In particular, all subsequential limits have a common one-dimensional marginals, and at least one of them is scalar. And the intuition is that basically you take consider kind of some massive diagonal argument. Take all intervals s, t where s and t are rationals, all s and countable convergence determining class, and pass to the epsilon going to 0 limit around some diagonal sequence where it goes to for all of them. And in the limit, you will have that take the unique viscosity solution on s, t for all possible f, and you can basically argue with this theorem that it will have that form PTY HT. And then the fact that these transition kernels you cooked up to satisfy Chapman homograph follows actually from the limiting argument because U epsilon f satisfies it. So as epsilon goes to letting epsilon go to 0, the limit also satisfies it. So you extract Taylor solution. So this Anubu Sumitreddy, this smart guy, with him, this improved this actually improved it vastly. The Taylor's solution is the unique limit in law, and there are multiple things. One of them was actually a trivial improvement. We just recently I just missed noticing that once we have the convergence of two-dimensional marginals, because the uniform going to finite dimensional marginals is not hard. But the hard part was the extending the conditions. So with Suresh, we just took the off-the-shelf conditions from this sort of standard reference for the user's guide to viscosity solutions by Randall and P.L. Lyons. We just took it off there as well. So somewhat contrived in this setup, all those conditions. So the situations where they are applicable were fairly limited. But the thing is that he managed to push this for a much more general condition for. And see, the strange thing is that backward Kolmogorov equation is a linear equation. The viscosity solution theory were developed for Hamilton-Jacobi equations. But somehow we couldn't find anything ready which we would just plug in. We thought it should be possible, it isn't true. So we had to use some very recent developments, specifically some PhD thesis from 1922 or some, sorry, 2022. I'm an old man. So 2022 from University of Toronto, and of course the classic work of Fleming and Sommer, combination of that. And he managed to give some conditions under which is vastly better than what we are doing. And there's some header continuity conditions of the coefficients which he, he has, and that kind of generalize this significantly. And this is what I call the anticlimax. These are the conditions, don't read them. I just leave them if you want. But I feel that this is the approach seems so natural that it should work fairly broadly. Just that the PD side is missing. Probabilistically, one knows why it should work, what to expect, and so on. But discovery solutions, people are coming from with different motivations have just ground uncovered. So that's where it stands. The future directions, of course, can go to the rest. Of course, we have seen this OD literature is full of exotic counterexamples. So we also positive and negative examples from the OD literature. So one is the conditions are questioned, and the dream would have been to do extend this for controlled diffusion, which is hard because viscosity theory there's not much of it for measurable coefficients. And control you cannot work with continuous coefficient, but typically controls will be measurable. Sort of what they call bang bang. It's quite common to have optimal control which are discrete. And then if you have a purely probabilistic tool to bypass all this, and then you so this is a glimpse into a future life of Rahul and Aisha. You have to do the correct mapping from corporate to academic.
We have questions, time for questions and comments, so please feel free. If nobody asks questions, Rahul has to.
No.
Where did you find this? Did you just draw this?
No, I googled for it. It's probably illegal to use it without their permission.
Yeah, it's written there.
It's written there,
Yeah.
the watermark.
Cartoons.
Stop.
Stop.
Oh, stop. So that would.
I think you are supposed to pay them for it.
Is it?
I think that is some of them are.
No,
Not all
stop
of
things
them are
are stop things can be used.
Stock is free, is it?
I think that's what I
Wait a
heard.
second. This is going live.
This is going live.
Quickly take it off. Next page.
But live to nobody. Nobody is watching it.
I'm not using it
That's
for
a AI.
commercial
AI will
purpose.
catch.
That is-
Not for a commercial purpose.
That is
No,
true. Then
no
it's fine.
financial gain.
Then it's fine. Okay, any serious question or comment? Other than moment
So, regarding the probabilistic proof, what is your intuition? Like, why should there be a probabilistic proof?
Yeah, hard to say. So it's basically
Because there are-
uniqueness of solution which is needed.
Yeah, but it's always very tricky.
See, if you go to viscosity solutions, you're always in the realm of PDEs.
Yeah.
Yeah.
So then you have no recourse.
Yeah. But there could be some other reason, pure Markov process reason.
It should be.
Some kind of a coupling or something
Yeah,
with
right,
the
exactly.
epsilons.
Anyway, what consequence of the PD technique I forget which journal we sent it to. Wherever sent it to probability journal came back it's too much PD. That's why it's applied
That's why there
mathematician
should be a
optimization.
probabilistic proof.
That's why it's
That's why-
ultimate dream.
Yeah, that is.
Ultimate dream. He said.
Was this post-retirement? This one, with the last paper?
No. Yeah, okay. Not post-retirement, but I have that emeritus position.
Okay. But that's retirement.
Yeah.
Yeah, so after 2022, not 1922. Retired.
Okay, so let's thank you again. So we have to set up the next stop.
So this is yours.
So the next speaker is Professor Ravi Mazumdar from the University of Waterloo. And the talk is being set, so we'll take a minute or two for that.
Okay, so let me use that time to first of all say I'm very happy to be here after coming very early this morning because of what you know is happening in the Middle East. So all the flights are chaos, and because they have to avoid Iran and all that stuff. It takes much longer, and all the flights. So anyway, I'm very happy to be here, especially to celebrate Rahul's impending retirement, and I will be retiring on the 1st of January, so it's not too far. So maybe I will have a leg up from Rahul on what post-retirement is. We know from Vivek that he can still solve and manipulate viscosity solutions. So let's hope I can be able to do such things post-retirement. So yeah. So my talk is going to be very different in flavor. I didn't want to. I didn't know thing, but it's a recent problem that Rahul is very well aware of. This is a problem that arose in an application that we were trying to study. Is it? I'm not loud enough?
No, for the room fine, but for the recording, that's it.
Okay. So this is a problem that I have been intrigued by purely because, while seemingly very easy, the intuition can be very hard to show, and we were recently able to succeed on it. So it's a model that arises from a parallelization application, and the motivation is the following. Okay, it's really many jobs processed in data centers today are highly parallelizable. What do you mean? You can break down the jobs into smaller jobs, and execution of those smaller jobs takes less time, right? And so, if you can find a job, the way to break it up and parallelize it and process it at the same time on various servers, because the server farms typically have 150,000 servers, 160,000 servers. That's a typical server farm. Then you can get a great speed up when you have these parallelizable jobs, and perhaps these are sometimes called moldable jobs, and they can run on a flexible number of servers. But of course, there's a maximum limit to which how much you can break up a job. And the reason is that when you break up a job, or think of a packet, breaking it up, it always has a header and a tail part. And if you break it up to such an extent that the consumption of the header and the tail part of the packet takes too much processing, then it's not worth it, right? So there's a maximum sort of limit to which you can split these up. But what we know is that within this limit, the more servers we give to a job, the better it's going to be faster. Okay. So the question is, how do we do it? And so the idea is that there is always the speed up function, and it's not always linear. All we can say is, so this is a typical type of application that I'm going to think of. So the speed up function measures the acceleration of a job's execution time, and it's typically concave, strictly increasing, because the more the servers you can give to a job, so split it up into smaller jobs, the faster you're going to get. But it's because there's diminishing return because of these sort of headers and so on. And so I will talk about two cases where speed up function is linear, which is the ideal case, and non-linear. So think of a server where you have 6 servers. Job 1 is just running on 2 servers. Job 2 is running on 3 servers, and there's 1 additional server available. So if a new job comes, you can't really split that up, right? So the question is, but on the so let's go back here. So if we allocate this server to a job, then a new job that comes while these jobs are being executed is going to be lost. So there's a trade-off between allocating too many servers. It reduces servers availability for future jobs, And in some sense, in the way the systems are designed, if a job comes and the number of servers are all taken, then the job gets blocked. So this is the assumption that is made. And the optimality criteria in these systems is therefore to minimize the average execution time and guarantee that almost all jobs find at least one, right? Because you don't want jobs to be blocked. Okay, so the question is, how do you allocate servers to multiple jobs such that the execution time is minimized while ensuring no job is lost? So let us look at it. So the system we consider as n servers. Each server can process only one job at a time, and each job can run on any number of servers, say 1 to dn, where I'm allowing the number of servers on which you can run also to be a function of it. It is no loss of generality. And the jobs inherent is an exponential random variable with unit mean, and its execution time decreases by a factor si if it is allocated I servers. So the speed up function is increasing, and so we'll assume S0 is 0 and S1 is 1 up to SDN, where SDN is the speed up achieved when you have D servers allocated to that job. And you assume that it's concave with this sort of concave function. So, and it is strictly increasing, and this is the typical sort of speed up function that you would get. Concave function with diminishing returns. And if it were linear, then you would just get this function. Okay. So for linear speed up, SI is equal to I, and sublinear speed up, we strictly assume that SI is less than I. Okay, so now the model we try to do generalize is that models, so jobs arrive according to Poisson process with some rate n lambda n, where lambda n is 1 minus beta, and this should be n raised to alpha, but it has not come out, for some beta greater than 0. And the reason is that this allows us to model a wide range of situations. So for every n which is finite, the arrival rate is less than 1 on, and as n goes to infinity, basically the load goes towards 1. So that this allows you to capture a wide range of phenomena that you need to deal with in server farm applications. And upon a job arrival, if no server is found, then the job is blocked, and otherwise the server allocation scheme determines how many servers to allocate to the job. So let us try to. So this is the typical thing. You have 3 occupied server, job arrives, if it's allocated 2 servers, it has job S2. If you have another job that comes, it can be allocated in 1 server, so it's allocation speed. So now let's try to model the whole system. So let XIT denote the number of jobs running on exactly I servers at time t. And therefore, the number of occupied servers in the system is summation IXI of t at any time. And therefore, what is the rate of departure if it's occupying server? If it's occupying I servers, then we know that the speed up function is SI, and so therefore the rate of departure is SI times XI of t. For all these, this is the total rate of departure of jobs from the system, and then you take kind of this fluid approximation, which is xi, the little xi, which is capital Xi divided by n. Q1 is Q1 by n, and these are the departure rates. Okay.
The battery is not working or something? Press the down button.
Maybe the battery is gone.
Down button working or not?
Yes, this is working.
Okay, I can do it from here.
Does it work from there?
Yeah, from the keyboard.
This is last page?
No, consider it.
Okay.
This is what.
Okay. So now let us just analyze the system back of envelope. What we know is that the rate conservation law says that if these
Symbols are missing.
the minus signs are not there.
Yeah.
So lambda n times 1 minus p n, this is the rate where p of n is the blocking probability of the system. Lambda times 1 minus p n should be equal to the rate of departures. Okay, so this is the first equilibrium law of the system. This is just a flow conservation. And the second thing, therefore, if there is no blocking, so if Pn is equal to 0, we know that lambda n must satisfy this. Okay? The second thing is that if, again, a minus sign is missing over here, if lambda n 1 minus Pn, so this is Little's law, so the rate of arrivals, average rate of arrivals times the average delay must be the total number in the system, which is the summation of all those little xi's. Okay. And therefore, again, under zero blocking probability, because this is what we'd like to achieve in the system, we know this simple relationship must be. Okay. So therefore, you can think of this idealized optimization problem that you want to do is minimize expected value of xi n divided by lambda n, that's the average delay. Subject to these flow constraints, subject to these because we've normalized everything, the number of occupied servers is less than 1, and we know this is greater than 0, and this must be true for all I belonging to 1 to d. Okay. So now let y star denote an optimal solution to p, and we say that our solution is going to be optimal if xn minus y star, and I don't know why all these negative signs have disappeared in the PDF, as n tends to infinity, then we say it's optimal. Okay. So the first thing is, let's try to understand that optimization problem a little. It turns out that if the speed up function is strictly increasing and convex, then this optimal sort of idealized situation that we'd like to reach is that if lambda n, the rate of arrivals, average rate of arrivals, is smaller than s dn by dn. So think of, suppose s were linear. So it would be s dn would be just dn divided by dn. So if lambda is less than or equal to 1, then the optimal solution y star of that optimization problem is that all the server occupancies up to d would be 0, and there would be all servers would, the system would operate where all servers, that means d servers are occupied all the time, okay, by the jobs. On the other hand, if this is the more interesting thing, is if lambda n belongs to si plus 1, then we know that there are two optimal solutions for this. So you think of it, the server occupancy process is the number of jobs occupying one server, two servers, up to d servers. So this is a d-dimensional Markov process, and basically what it says, in the idealized solution, either you should have the entire probability concentrating where all d servers are occupied, or perhaps two servers, I and I plus 1. Okay. So the question is therefore we know that the solution to this optimization problem is at least is at most 2-dimensional. So it's 1 or 2-dimensional, depending on the speed up function that you have, okay, in your system. And any system scheme which aims to achieve asymptotic optimality must exhibit, therefore, a state space collapse in the limit. and therefore lambda n belongs to this, then only two possible states are possible: servers which have I jobs running on them, or servers having I plus 1 jobs running on them, and hence the fraction, the SI yi by lambda n of jobs should receive I servers, and the rest should receive I plus 1 servers. And the question is to understand whether you can devise a scheme. And so suppose you take a probability vector of this type, and the goal is to allocate I servers with this probability if there are at least I servers available in the system, or you occupy it. And again, a greedy scheme of this type, so a job arrives, you look at how many servers are available. If I servers are available, you give it to them, or I plus 1, you give it to them with these probabilities, and otherwise, they take whatever number of servers which is available, as long as the number of servers is less than bn. Okay. So in the special thing, we call this just a greedy. I don't know why this PDF is having this problem. Okay. So now assume that lambda n is equal to 1 minus, let's call it beta function of n, for some beta greater than 0, and assume that dn is little o of n, then what one can show is that the actual process converges to this idealized solution as n tends to infinity. And what that implies is not only is the blocking probability going to 0, but the delay converges to this best delay that you can get out of the system for the system thing, and in such a state, this scheme is optimal. And you can get finite time bounds and so on, and the rates of convergence, and the rates of convergence are of this order. Okay. So if state space collapses in one dimension, then the rate of convergence is O as 1 square root of n, and if dn is so it's again one dimensional, then the rate of convergence is of the delay is of the order of 1 by n. Because we are interested to know how large should the server farm be, and what would be the performance that we would be expecting. So the idea of the proof is what? Is a kind of a Stein. It's really using Stein's ideas. Is that you try to couple the generator of the Markov process with the generator of the differential equation or the fluid limit that we talked about earlier. Let's see. Okay. So think of the deterministic fluid limit. Xi dot is lambda I minus pi xi, because is the rate at which arrive. Pi si xi is the rate of thing, and this should be also minus sign. And the goal is to match this mean field limit. So when it is d, it's just si yi star minus si xi. Otherwise, it's lambda this. And the goal is to match this mean field limit. And so if you look at the generator of the Markov process X and L to be the generator of this differential equation, the idea is by exploiting the equilibrium measure, the expected value. I don't know what's wrong with speed. So I'm really sorry. The expected value of the generator operating on any nice function is going to be 0, and then we have to compute, in some sense, the difference between these generators and show that as n tends to infinity, you get this convergence. It is classical Stein technique. And so you think of this Lyapunov function as xi minus yi star squared. You pick a Lyapunov function of this type, and you can write it again minus yi squared. You can. I'm so sorry. I don't know what's happening to this video. Okay, it should be cix plus minus sign over here, and lambda I minus si y. Okay. And what you can show is since the expected value of g, v of x is equal to 0, when you apply the Stein sort of law, you can bound the Lyapunov function by something that decreases to n plus some rate r being greater than lambda, and q1 is 1 minus this. Getting completely lost. So the question is that one can show that this Lyapunov function, by using this Lyapunov function, that the difference between by the way, I will give you a proper version of this PDF when I can get a chance to work on EduROM and get that. You can that the difference between the generator of the Markov process and the generator of the differential equation go to 0 in L2 norm as n tends to infinity. And so this is sort of the state space collapse idea that takes place, that you see what happens is that if you have this yi star, is that this is the line, straight line, and this would be the equation S1 plus S2 is equal to lambda, which is coming from the equation from the flow equation. And what it says that this is a case, of course, where you have a unique point. There will be a unique point at which the maximum will be achieved. So just to conclude, I want to just give you that how do we, when you simulate these systems, does the theory bear out for large n? And so this is typically the number of processors, and you see what will happen is if you have sublinear functions and beta equal to 0.2 and alpha, beta, so sorry. You see what happened is, again didn't come out, is we choose lambda is 1 minus beta upon n raised to alpha. Okay, so this is the kind of rate at which you arrive. And the reason is that you choose an arrival rate of this type, because if you choose alpha equal to half, then this is typically called halving regime. This is a regime which is like a diffusion limit regime that you want to study. And so we study this problem for various values of beta and alpha. And what it shows is really you get the required speed ups that you want. Sorry, this is the delay, and this is the blocking, and the blocking starts going to 0. And this curve shows what happens if you have this nonlinear speed up, but you decide at every time to allocate these servers. That means if these servers are available, you just give D. If fewer than D servers are available when a job arrives, you allocate the number of servers that is available. So that's the yellow line. So what it shows is that clearly this is not an optimal thing to do. You have to, when you have sublinear speed up, you have this Markov process that concentrates on 2 states, and you have to try to find a probabilistic algorithm if you try to get you there. And this is really to show that since we are working with a loss model, these loss models turn out to be insensitive. So we assume the service time distributions to be exponential, but it's not necessary. The reason is if you take linear speed up, then there's a very interesting phenomenon that takes place. That if you look at these systems and you say that I arrive, I look at the number of servers available. If the number of servers is D or more, I allocate D. If the number of servers is less than D, I just take whatever server is available. If I look at that scheme and I look at the limit of that system, that system is going to concentrate on a state space where you always allocate these servers or you get blocked. Okay. And so in that case, we know that is what is called a multi-rate loss system, where every arrival requires D servers, and if it cannot find D servers, gets blocked. Then we know that such systems are insensitive. That means they do not depend on the service time distribution. And so the belief is, of course, that this system also is insensitive. So the service time distribution does not matter. And these are sort of simulated. We haven't proved it as yet, because the proof is not, is going to be rather hard. But just to show you that this insensitive kind of phenomenon takes place when you assume exponential deterministic mixed line operator service times for jobs. Now, there's one very interesting aspect of this problem which I have not so far hinted on, is that there is no simple or even there is no coupling technique that works on this problem. And the reason that these class of models have never been studied in the literature, purely because here you have a system where the service time, the service duration changes with the number of servers that you have, and the number of servers that you have depend on therefore the number of available servers when you arrive. Okay, so such a system is there is no simple coupling argument that allows you to show that the state space collapse works, and therefore you have to work with. Actually, I just took one. I showed you the case of one Lyapunov function to get certain bounds to couple the generator of the Markov process and the generator of the fluid system. But there are more Lyapunov arguments required to show that each one of those terms goes to zero. So you have to develop multiple level of Lyapunov functions, and this is really this is a question of a proper choice. Okay. And so this is again to show that if you have linear speed up, sublinear speed up, and so on, you get the same type of thing with blocking probabilities. Where the blocking probabilities, you see, are with 4,000 servers. This is the order. You want the blocking to be zero, but simulation show that the blocking is very low. So the limit must go to zero. So what we have is we devise a server allocation scheme that minimizes mean execution time and asymptotic, non-asymptotic bounds and results and simulation results, which really demonstrate that this theory works very well. In fact, Google has a scheme which they provide for people who want to run jobs involve machine learning, which uses this type of analysis. And it sounds to be insensitive. And the clear future work is to show this thing that the system is insensitive analytically, but also to devise a scheme in which we do not need to know whether lambda n, the arrival rate, because we don't know this, whether it arrives between SI, DI and SI plus 1 and DI plus 1. So if we don't know where this arrival rate sits, we do not know what are the probabilities to do the probabilistic algorithm. And so the question is, can you learn this? And actually, one can devise a very, very simple algorithm to learn this without knowing this SI by DI. So without knowing the speed up function exactly, you can get to these optimal points by just measuring things. Okay. And another very interesting take on this problem, which we have solved, and I have not presented the results, is suppose you don't have access to all the servers. You don't know the server states of all the servers. Suppose you sample a finite number of them, right? Suppose you sample kn number of them, and then you make the decision. Out of the sample, you apply this law, this rule. The question is what happens? How large should kn be, and so on. And one of the things that you can show is that if the speed up function is linear, then this number kn, as long as it's greater than dn, it can grow as slow as you, as long as it grows close to you. And so with that, again, this is to keep you all alert. Okay, so with this I want to stop, and I would like to say how much I have enjoyed my friendship with Rahul. We first met, I think, in 1987 or so, when he came to visit a friend of his at Columbia. You at Duke.
No, you came to Cornell.
No, I no different. I didn't come. You were at Duke at that time, and you came to New York because this guy was there.
No, Vijay. No, you had come to Cornell. We sat at a bar. That
Correct.
was the first time.
First time.
When
And the
you had
second
joined
time,
and I was a student. And then
and the
at home.
second time we met was we bumped into each other in Paris. He was with
No. Before that, there's another story. It's a brilliant story.
yes,
In '96, Krishnamurti had these conferences.
right.
I had just written the book with Ronald, Mr. Kumar was standing in front of me, P.R. Kumar. We were waiting for food. And Ravi behind me. So P.R. Kumar looks at me and says, "What's your name?" I said, "Rahul." He said, "What do you work on?" I said, "Percolation." Then he says, "Have you seen this book by, have you seen this book called Continuum Percolation by Mr. and Roy?" So I said, "Yes, I have." Ravi behind me starts laughing, okay, because I had seen the book. Ravi starts laughing, doesn't know what to say. And so Kumar asks Ravi, "Why are you laughing?" Because so he wrote the book, he's better seen. This is '96. And then we bumped in Paris.
In Paris, where we almost missed our flights.
Right, exactly.
Because we went to the park, Jardin
Yeah, the
Luxembourg,
other state.
Luxembourg, and then we were talking, and then we suddenly realized we rushed to the metro, and then we missed the
Yeah.
change, and we went all the way to the end,
Yeah,
and I had to come
yeah.
back and so on. So we almost missed our flight. I think he was going to Italy, I was going somewhere else.
Yeah, we were, yeah.
Okay, so with that, I have many good memories, and for the past 10 years or so, Rahul has always taken time to come and visit me in Waterloo, and I've really enjoyed those visits. And one of the things, of course, he did when one of his visits was this work on these models that
Yeah, with Mamunti
spoke about, which are these kind of we looked at various versions of opinion dynamics, where with certain probability you change opinions and so on, depending on this, and we looked at a fully connected network. And so that was a very fruitful work. But Rahul had been also a mentor to a lot of my PhD students, including one of the authors of this work, Arpan Mukhopadhyay. And so I
He got a job here, but our director didn't allow him.
Why?
Because he wanted an extension till June because he had this.
Oh yeah, fact.
But then,
but that was ISI Calcutta, I think.
right.
Yeah, he was almost going to join ISI Calcutta, and then they didn't give him an extension. So he had been a great mentor to Arpan, and except for this COVID period when Rahul could not come, and more recently due to this India-Canada spat, he almost could not get his visa. He has finally managed to get a visa, so hopefully I will get to see Rahul for a few weeks when he comes to Waterloo.
Yeah, and I don't need to take leave from ISI.
Yeah. So thank you very much for all your friendship, and it's been a great ride, and I've learned a lot from Rahul. Thanks a lot.
Thank you.
Any questions or comments for Ravi?
So this sampling of KN, as you said, there coupling should work, no? Because
nothing works. Because it comes down to boiling to the same type of issue that there is no monotonicity in the system purely because your service times are changing with the state that you see. You see, typically in loss models, even multi-rate loss models, you have a number of type of arrivals, but each type of arrival takes a fixed number of servers. But here, the number of servers that you take depends on the state that you see in the system, and then the service time changes. So because of that, you don't have any monotonicity.
Any other question or comment? Okay, so if not, then let's thank Momanti, Vivek, and Ravi for giving really nice talks and starting this conference in the right spirit.
I'm sorry about this PDF. I have to figure out what's happening to the PDF. Why the E's, the A's, the
alpha.
Brackets, first brackets are missing.
But
why they're all these
Some letters, some characters are missing.
every page has a different character
missing. Exactly. I don't know what's happened.
The set is fixed. I know
It may not be the PDF, it may be the compatibility of the PDF.
But PDF is supposed to be good in all
You can
systems.
check the same PDF in your laptop.
No, in the laptop it's okay.
And that's
Yeah,
like
so
in
maybe the
project.
compatibility.
I'm making it. It happens sometimes.
But it's the same PDF.
Yeah.
No, it's
Yeah, because PDF C, PDF.
system was stable, but it's still there are problems. So now we have a break.
Yeah, we have a break for half an hour. Please come for tea or and some snacks in front of the guest house.
Where is urban going?
He's at what?
He's a moderate.
Rahul, this is something for you to celebrate.
Thank you.
Thank you.
Well.